How to solve circuits the right way and the joys of circuits analysis. In Lecture 4, we continue to work out examples of the extra element theorem. These examples and more can be found in my book, Fast Analytical Techniques in Electrical and Electronic Circuits, published by Cambridge University Press and available online from any bookseller. In this video, I'm going to work out 4 examples of a reactive bridge circuit with a capacitor. I'm going to work out 2 different voltage transfer functions, an input admittance, and a reactive bridge circuit with a right half plane 0. In our first example, we are going to determine the voltage transfer function of this reactive bridge circuit, V0 over Vin, in which we are going to designate C1 as the extra element and apply the extra element theorem. We are going to take C1 out by considering its impedance to be infinite, or looking at the circuit at 0 frequency, or equivalently its susceptance equal to 0. And when we do that, we obtain this circuit here, where the capacitor is an open circuit. And the voltage transfer function, V0 over Vin, is given by the voltage division between RL and the parallel combination of these resistors, which can be written right away by inspection, as shown here. RL divided by RL plus R3 in parallel with R1 plus R4. We now have 2 additional calculations to perform. The first one is the ordinary impedance looking back into port 1 with the excitation set equal to 0, which means we place a short. And we obtain this rather simple circuit in which we see that Roman R1 is given by R2 plus R1 in parallel with R4 plus R3 parallel RL. You see that from this circuit. First thing you see is R2, and then R1 is connected between this point and return here, so it's R1 in parallel with R4 in series with RL parallel R3. R3 is in parallel with RL because this node has been shorted to the return. Next, we calculate the null impedance looking into port 1, whereby we connect a test source across port 1, and that test source, along with the input or the excitation of the transfer function, will null the response of our transfer function, which is V0. So Vt and Vin together will null V0, make it go to 0, and as a result, the current going through RL will go to 0. Now, we don't have to carry R2 through our calculations here, because we see that script R1 is R2 plus whatever comes after it, as shown here, and so we go with whatever is after it and keep R2 out of the picture. When we do that, we take R2 out and replace it with a short, and we see in this case now that R1 is slightly easier to determine. Now Vt appears directly across R4 because V0 has been nulled. And that means that the current through R4 is Vt over R4, which when it reaches this junction here, turns around and flows through R3 and creates a voltage drop across R3 given by Vt over R4 times R3. Now the sum of the voltages across R4 and R3 will appear across R1. And that means that we know what is the current through R1. It's this voltage here divided by R1. And we can write now the test current IT is Vt over R4 plus this current here, Vt over R4 times R3 plus Vt divided by R1. And now we can solve for IT over Vt or Vt over IT, which is the simpler script R1 calculation. You see that here we have 1 over R4 plus 1 over R1 scaled by or divided by R3 over R4 plus R1. So it's the parallel combination of R4 and R1 divided by 1 plus R3 over R4. And we substitute this in here, and we find our null impedance looking into port 1. And that's it. And these are the 3 calculations that you need to perform. And now we substitute our 3 independent calculations in the extra element theorem, H0, script R1, and Roman R1, and we get our transfer function in factored pole zero form, in which H0 is that voltage divider. The 0 is given by 1 over C1 times the script R1. That's our 0. And our pole is 1 over C1 R1, Roman R1. That's our pole there. And you're done. This is how you analyze a reactive circuit, simply by analyzing purely resistive circuits. 3 independent, small resistive circuits, rather very easy to analyze, and you get your full-blown transfer function in a very meaningful form here. In our second example, we're going to use the same bridge circuit, except that we're going to take the response across R3 instead of RL, and we're going to determine the voltage transfer function V0 over Vin. We know that this should have the same denominator as the previous one because it's the same structure. When we set the excitation equal to 0 in this case and in the previous case, we get back the same structure. So the both transfer functions here must have the same denominator. And it's only the 0 and the low frequency asymptote that are going to be different. As before, we designate C1 as the extra element, and we designate its impedance to be infinite. Get this circuit here with port 1 open, and the transfer function V0 over Vin again is given by a voltage divider, which in this case is going to be R3 in parallel with R1 plus R4 divided by this parallel combination with RL. Again, as before, we have 2 additional calculations to perform. The first one is the ordinary impedance looking into port 1. This is the same as before. It concerns the denominator, so it is the same as before, as we discussed a little bit earlier. And we need to calculate now the null impedance looking into port 1, in which Vt and Vin together will null the response across R3, and as a result, the current through R3 will go to 0. And as before, we don't need to carry R through our calculations. We can just take it out and determine the simpler impedance looking into port 1 and add that to R2. And when we do that, we see that Vt appears directly across R4 and RL, and there's no current going out of this branch here. It's just dangling there doing nothing. So really all the current through R4 goes to RL. So I have a very simple circuit with Vt connected across R4 plus RL, and therefore the voltage drop across R4 is going to be nothing more than the voltage division of Vt between R4 and RL, which is Vt R4 over R4 plus RL. Now, since V0 is equal to 0, this voltage here appears directly across R1, gets copied over it. Same thing. And now I know the currents in R4 and R1. This one is going to be Vt R4 over R4 plus RL divided by R4. Well, I knew that to start with. And this current here is going to be Vt R4 over R4 plus RL divided by R1. When I add the two together, I will get IT. That's it. So I know what is Vt over It in this case. When I do that, I get this expression for Vt over It. And I can substitute that in here, and I will have calculated my null impedance looking into port 1. And now we are going to substitute our three independent calculations in the expression of the extra element theorem and get our transfer function in factored pole zero form, in which H0 is given by the voltage divider, the 0 is given by the reciprocal of the time constant formed by C1 and the null impedance looking into port 1, which results in this nice, meaningful, neat expression for the 0. And the pole is given by the reciprocal of the time constant formed by C1 and the ordinary impedance looking into port 1, which is given by this meaningful answer here, in which the circuit elements, the resistors, are grouped together in meaningful form. And that's it. You've analyzed your second transfer function, again, only working with resistive circuits and getting neat, clean, meaningful algebraic answers. And finally, for the same circuit, with that same excitation, we want to determine the input admittance. So this is our third transfer function that we would like to determine. And we recognize again immediately that the denominator of this transfer function is the same as the other two, because when we set the excitation equal to 0, we get back the same structure as in the previous two cases. So now we're going to apply our extra element theorem to the input admittance function, in which we again designate C1 as the extra element, and we set its susceptance equal to 0, which means we put an open there, and we determine the value of the input admittance at 0 frequency, which is the reciprocal of the input resistance, and we have Y in 0 as 1 over RL plus R3 in parallel with R1 plus R4. That's our first calculation. And we need to perform two additional calculations. And we have two additional calculations to perform. The first one is the ordinary impedance looking back into port 1 with the excitation of our transfer function set equal to 0, which means it's a short here. And this is the same as before, as we discussed, because it's the same denominator. Anyway, it's a very simple calculation. It's done it before. It's R2 plus R1 in parallel with R4 plus R3 parallel RL. The second one is the null impedance looking back into port 1, except now the response was the current coming out of this excitation here. And when we null the current through an independent excitation source, voltage source here, that's equivalent to opening that port there. We discussed this before for impedance functions or admittance functions. So the null impedance looking back into port 1 is determined by opening that input port there. And this is a simple calculation, just like the first one, except that this one is going to be R2 in series with R4 in parallel with R3 plus R1 and in series with RL. And that's our script R1 looking back into port 1 with our response nulled. The response in this case, remember, is that of the input admittance function, which is the current coming out of the excitation connected here, the voltage source. And when we null that current there, we talked about in the proof of the extra element theorem that that is equivalent to opening that junction there, that port there. Maybe you want to go back and again review that. So when we substitute our three calculations for Y in 0, script R1, and Roman R1, this time we get our input admittance in factored pole 0 form, in which Y in 0 is what we calculated there, and our 0 and our pole, which we calculated almost by inspection. So we have essentially determined the input admittance of that bridge circuit just by inspection, inspecting three simple resistive circuits. Each one of these calculations were trivial. In this last example, we are going to determine the voltage transfer function of this bridge circuit, in which the voltage V0, the output, is taken across the bridge resistance RB. Once again, we will designate C1 as the extra element and apply the extra element theorem. We will take C1 out by considering its susceptance equal to 0 or its impedance equal to infinity. We take it out as shown here, and we determine V0 over Vin, a very simple calculation for this resistive circuit. Here I'm showing how you can take the Thevenin equivalent of R3, R1, and Vin and write a single voltage divider, and for that you get the transfer function V0 over Vin. And now we have two additional calculations to perform. The first one is the ordinary resistance looking back into port 1 with the excitation of the transfer function set equal to 0. And this we can write by inspection, because you notice that this point here is the same as that point there. So looking into R1 means you're looking into R2, and looking into R2 this way, you see R2 in parallel with R3 parallel R1. There it is. R3 is in parallel with R1 plus RB. That's for Roman R1. Next, we want to determine the null impedance looking into port 1, whereby Vt and Vin will null the response across RB, the voltage across RB, so that the current through it will go to 0. And now we will do the algebra on the circuit diagram to determine Vt over It to get the null impedance script R1. Well, we see that once this current goes to 0 and this voltage goes to 0, then It, the current that's flowing through here, will flow entirely through R2 because there is no current in the bridge. It's been nulled. And it creates a voltage drop across R2, which is ITR2. Now, since the voltage across RB is 0, ITR2 gets copied across R1. And it will start a current through R1, which is ITR2 divided by R1. Once again, that current will flow entirely through R3 because there is no current flowing in the bridge. So it will create a voltage drop across R3, which is that current multiplied by R3. But the voltage across R3 is also the same as Vt. This voltage here is 0. Vt appears across R3. So Vt equals to the voltage drop across R3, which is given by this current here, which is ITR2 over R1, ITR2 over R1, times R3. And we see that the null impedance, or the null resistance looking into port 1, is negative. And now we can write our transfer function. And now, when we substitute our three independent calculations in the expression of the extra element theorem, once again we obtain our transfer function in factored pole 0 form, and we see that the 0 is a right half plane 0 because the null impedance looking into port R1 turned out to be negative. And here are the expressions of H0, the right half plane 0, and the pole. That's it. Again, we've analyzed three simple resistive circuits in order to obtain the transfer function of a reactive bridge circuit. Now the question is, how come this 0 turned out to be a right half plane 0? Can we physically interpret the fact that this is a right half plane 0? Yes, we can, and we'll see that in the next slide. We see here that at low frequencies, when we look at this circuit, the voltage transfer function V0 over Vin with this polarity is positive, given by this expression here. When we look at it at very high frequencies where the capacitor is essentially a short circuit like this, we see that RB appears in parallel with R3, but the positive polarity of V naught gets connected down to the return of V in. And at very high frequencies, you have basically a voltage division between R1 and RB parallel R3, in which the polarity of V naught across RB parallel R3 is inverted, appears inverted with respect to V in. The positive end of it comes to the return end. And that's because we have two paths from the excitation to the response. One that is dominant at low frequencies, it's a non-inverting path, and one that is dominant at high frequencies, which is an inverting path. And the right half plane 0 is the one that takes care of it. As you can see in this expression of our transfer function at very high frequencies, where the capacitor begins to act like a short circuit, the one term dominant drops out, and you're left with a negative real transfer function at high frequencies. That's why we have a right half plane 0. We have two paths from the excitation to the response. One path which is dominant at low frequencies is non-inverting, and one at high frequencies which is inverting. And this is the end of the examples of the one extra element theorem. And next we're going to move into the two extra element theorem. Thank you.